So in this section of this video tutorial, we will show you how to read from an MRAM memory. So let me just draw one MRAM memory cell. So this is the MTJ, and this is the bit line node, and this is one transistor. This is the gate of the transistor, and this is source line. So we will try to read from this memory. So to do that, at first connect the VPN. I mean the Ivanti VPN if you are out of UT network. If you are not connected to the UT network or Wi-Fi, etc. And then you have to open the mobile external real VNC, etc. And I have created a separate folder for the MRAM simulation. So this is the folder, and nothing is here right now. So we need some files and codes to run the MRAM code. So let me upload those files from my personal computer. So I will use this upload feature of mobile start, and you can just use the real VNC upload feature if you are using real VNC. I am going to upload these files. So yeah, so it will take a few seconds to upload those files. And as you can see, these are the files. So here we will try to read from the mram read.sv file. So let's open the main file. Here, main file, I mean the simulation file here is the .sv file. So let me just open that file in G8. I'm trying to open the Gedit. From Gedit, I'm going to open that file. Sorry. So here is the mram folder that I have just created, and these are the 4 files that I just uploaded. So let me open all of these files maybe. Not all, just these 3 files. Okay, then this is actually our main code, the mram read.sp. So this is our main code, and here as you can see that it is calling 3 files, 3 external files. The first one is the mtj model.va. Let me just show you the folder. So here as you can see that so these 3 files must be here in the same directory. Okay, so let me check. So we need mtj model.va file. So we do have the mtj model.va file in this directory. We need ptmmg model file. So we do have ptmmg model file, but currently this is in the zip format. So we need to unzip it first. So let me just unzip it using the command unzip and the file name. I've already shown you how to unzip any zip file in the very first video of this class, and I have shown this unzipping procedure in real VNC as well. So let me just unzip. So it's unzipped. If I refresh, you can see that this is the pdmng folder. So let's go back to the code. So we do have pdmng model file in this directory, and we have device parameters.inc file. Yeah, as you can see, I have also uploaded the device parameters.inc file. So we will let you know what file does what, or we'll know the functions of these files later. But let me just skim through the code. So these are the options. You do not need to touch anything here. And let me go to the parameter or definition. Here, as you can see, that we have declared a variable called polar or POLR. The variable name is POLR. This is representing the polarity of the MTJ. Okay, so you know that MTJ has 2 states, parallel or anti-parallel. If the polarity of the MTJ is parallel, then we have to set POLR equal to 1. If we want to represent anti-parallel state, we have to put this variable is equal to 1. Okay, so let's go back. Let's go to the next section, which is the netlist. Let me just draw the circuit to describe the netlist. Okay, we have put them side by side, and let's analyze the code and the circuit. So at first, we have a node called BL. As you can see, BL, and a voltage source is connected between BL and 0. So the voltage source name is VBL. So let's connect a voltage source here. So the one terminal of the voltage source is connected to BL, and the other terminal is connected to ground or 0. Okay, and then let's move to the next line. Here, this is we are calling a model file here, as you can see. So the model file is we are calling actually this MTJ. So we need to go back to the first line. Here, as you can see, that we have called a model file which is called mtj model.va. So this line actually calling that model. Okay, and let's let's look inside the model file. Okay, so here is the model file. As you can see, uh, this model file has two nodes, right? The first one is FL and the second one is PL. Okay, so this is, suppose this is FL node. So this model, treat model as a black box. Okay, so this is a box, and this box has two terminals. The first one is FL and the second one is PL. So as you can see, the first node is connected, the first terminal FL is connected to BL. So we are calling a model, and we're naming it like this, something like the X, MTJ, PSTD, name whatever you wish, but start with X. And as you can see, the first node is FL of this model, and treat, as I have already mentioned, treat this model as a black box, and the box has two terminals, and the first terminal is connected to BL, and the second terminal is connected to NDX. I'm just named this node. Suppose this node named as NDX. So this FL is connected to BL, and the PL terminal of this black box is connected to the NDX node of this circuit. Okay, and then we have to pass the polarity, because we have to tell this model that which state do we want. Is it parallel or is it anti-parallel? So we are passing the POLR variable, and we have set POLR equal to 1. And I have already mentioned the model is written in a way that if we pass 1 to this POLR variable, it will understand that we are actually we actually want parallel state, and if we pass -1, the model will be calibrated to anti-parallel state. Okay, and then we can also pass some other variables like TOX. Here TOX represents the thickness of the MTJ, and the W represents width, and L represents the length of the MTJ. And as you can see, these are some parameter values. Okay, and here uh, and these are the parameter values, but as you can see, there are no parameter values mentioned here like TOX MTJ or WMTJ, and we have not mentioned another thing here. So in this voltage source, we are applying a voltage called V read. This is also a variable. I mean, this is also a parameter, but we have not defined the parameter here in this file. Where are we actually defining these parameters? Like these are also parameters, like right? TOX, MD, MTJ, W, MTJ, L, MTJ. These are also parameters, but we have not defined the parameters in this file. So why did we define? So remember, we have included a file called deviceparams.inc. So here is the file. So we are actually making a separate file where we are defining the parameters here. So why do we do that? Because if there are too many parameters, the main code looks actually messy. So to keep the main code neat and clean, we actually separated the parameter values in a separate file. And so all these variables are defined in that parameter file. If you want to change some parameter, just go to that file and just change them, and it will take that value. Okay, now let's move to another voltage source here. So we have another voltage source which is called DMTJ whatever. It's just a name, and it's connected between the node NDX and ND. Okay, so let me just redraw according to the code. So let me use this portion as well. So okay, so we do have a voltage source here which is connected between NDX and what ND. So there is another node ND. Okay, and we have set the voltage of this voltage source to 0. So this is set to 0. So this is just a voltage source which actually shorts the node NDX and ND. This voltage source is set just to measure the current. You know that yeah, in the previous tutorials, it has been demonstrated that we can easily measure the current through a line or wire by inserting a 0 volt voltage source, right? So this is the voltage source to just measure the current. This do not have any effect on the circuit. This is just shorting the NDX and ND node. Okay. Now let's go to the next line of the codes, which is XM1 PSCT. This is just a transistor. So let me put a transistor, and this is the drain node, which is ND, and NG. As you can see, this is NG is the gate node, and the NS is the source node. Okay, so this is NG and this is ND, and the body is also connected to NS. So I mean, body and source are shorted. As you know that we have to put the body of the NFET, I mean the NMOS, to 0. So we will apply 0 to NS node. So the body will also get 0 volt. Okay, so here as you can see the source, we have declared a source voltage here. As you can see here, we have connected a voltage source between NS and 0. 0 means ground. Okay, so this is 0 and this is NS. So there is a voltage source connected between the NS and zero. We are naming it V source, and we are setting this to zero. Okay, so this is just shorted. You can think that you can think it as a short circuit. Okay, so the 0 volt voltage source is simply a short circuit. You are just connecting NS to the ground. Okay, and then we have a V gate. We have to insert gate voltage to this transistor. So there is a voltage source right here. Okay, and this is also a 0 volt voltage source. So when you see a 0 volt voltage source, that is just shorting the nodes. Okay, so this is connected between NG and WL. There is another node which is WL, and there is NG, and this is 0 volt. So this is nothing but shorting between NG and WL. And then we do have. Uh, let's go to the next line, which is the word line. So here we are defining a voltage source, which is connected between WL and 0. So here we sorry. Here we are connecting another voltage source which is connecting between WL and 0 means ground, and we are naming it as VDD WL or something like that. And here this is and here in this voltage source we are applying a PWL. So what is it doing? Let me just draw a wave shape. So this is not a fixed voltage. The voltage is changing. So let me draw the wave shape of this voltage source that we are providing to the WL or gate of this transistor, because WL and the gate of the transistor is shorted. So let me just draw the wave shape that we are providing through this VDD WL voltage source. Okay, so let me just draw. So here, so this means at these are actually paired. Okay, so you can see some pairs. So this is the first pair. The first element is zero, which is the time. Always it's the first one is the time and the second one is the voltage value. Okay, so at zero you can read this like this. Okay, at zero you have 0 volt. Okay, so let me just put that here. So at zero time, this is time. So let me mention another thing that this is a transient response, I mean transient code. So that's why we have to insert a wave shape. Okay, so at zero, the voltage at y-axis we have voltage value. So at zero, the voltage is also zero. You can read like this. And next, let's move to the second pair. This is the second pair. So this means at 1 nanosecond, the voltage value is zero. Okay, suppose this is 1 nanosecond, and here the voltage is zero as well. Okay, so the wave shape is going like this. Okay, going like this. And then let's move to the third pair. Here, as you can see, at 1.03 nanosecond, the voltage value is PV. Okay, so suppose this is 1.03 nanosecond time. Okay, and at this moment, the voltage is PVDD. So suppose this is PVDD, and we have defined the value of PVDD in the device params.inc file. The PVDD is set to 0.9 actually. So PVDD is equal to 0.9. Okay, we have just said it. So at 1.03 nanosecond, the value is here. The voltage value is here. So the voltage will go like this. Okay. Now let's move to at four. Now let's move to the next pair, which is the voltage is like PVDD. The voltage value is PVDD at 4.03 nanoseconds. So this is 4.03 nanosecond. The voltage value is PVDD here as well. Okay. So we're maintaining PVDD up to 4.03 nanosecond. And then at 4.06 nanosecond, the voltage value is zero. Okay. So suppose this is 4 point, sorry. Suppose this is 4.06 nanosecond. And at this moment, the voltage becomes zero. Okay, so let me put a dot here. So voltage becomes zero. So how will it go to zero? Just like this. Okay. So it will go down linearly. Okay. And then at 7.06 nanosecond is also zero. So suppose this is 7.06 nanosecond. I'm not writing it again. So at 7.06 nanosecond, it's zero as well. So this kind of wave shape we are applying to this voltage source. I mean, this voltage source is providing like this voltage, this kind of wave shape to the gate, because this voltage source is zero. This you can assume this as a short. So basically, you are applying this kind of voltage wave shape to the gate of this transistor. Okay. Now let's move to the analysis section. Here we are performing transient analysis, and that starts with dot run. And here the first one is the step. I mean, at which step size you will be simulating the transit response, and the second one is the simulation end time. Okay, and we have put an alter command because initially we are reading the code. I mean, reading the MRAM memory when the polarity is one. I mean, when it is parallel, and we also want to see how is the current value of the MRAM cell when it's in anti-parallel state. So to compare this, we actually added an alter command where we are setting polarity equal to -1, which means it's anti-parallel. Okay, so the first portion of this code before the dot alter, it will generate .tr0 file. Okay, and for the dot alter command, it will run the whole code again with polarity value -1 or anti-parallel state, and it will create another result file with .tr1 extension. Okay, so .tr0 will show us the result with parallel state, and .tr1 file, the result file of with .tr1 extension will show us the anti-parallel state results. Okay, so let me just run this code. So just you have to just load HSpice like the very first video, and then you also have to load the wave view. So I have already loaded them. Like as you can see, I have already loaded the wave view, and I also have already loaded the HSpice somewhere in the beginning. So let me just run this code HSpice, and the code name is mram underscore read.sp. So as you can see, the info is HSpice job concluded. That means it ran successfully. And then now let's see the results. So I have already loaded a wave view. Now I'm just entering command wv space ampersand to open the wave view software. So let me open the waveform. And here, as I have mentioned, that we will have two files with the TR extensions. The first one is TR0 and the second one is the TR1. We will open both these files. Okay, so both these files are open. But before plotting any results, let me show you which current or voltage value should we plot. Okay, so let me go back to the whiteboard. So, so here, did you remember we had put a 0 volt voltage source to measure the current through this memory cell. Okay, so we need to see or observe the current of this voltage source that will represent the current of this cell. Okay, so as you know, that in the parallel state, the resistance of this MTJ is lower when this is in parallel state, and in that case, our current should be higher, right? So let me just write something. So our TR0 file is representing the parallel state. Okay, and our TR1 file is representing the anti-parallel state. Okay, so let me select the results. So here, so currently I have selected the TR0 top level file. I mean this thing, and now I want to see or observe the current through these voltage source, and we name this voltage source as something like this: V underscore MTJ underscore VSTD. You can name this anything actually. So uh, in this code, this is named as this. Okay, so the current value of this voltage source is showing the current through the memory cell. So let me just plot this. Yeah, I'm just like uh, okay, so I have plotted the current through this voltage source. Okay, so here is the current value. But before that, we can also plot uh, the word line voltage, because in the word line we have stuff like this kind of voltage wave shape. We can just verify that is it correct, or did we correctly provide this kind of wave shape to the word line. Okay, so let me just open this V word line. I mean the voltage of this word line WL node. Okay, so let me just double click here. As you can see, yeah, so we have been able to provide this kind of wave shape to the word line. Okay, okay, and now let's this is let me just delete this thing, because we have already verified that we have successfully applied this kind of wave shape to the word line. I mean, we have activated the word line successfully. So let's just delete this, because we want to compare the parallel state current and anti-parallel state current. So as you can see, this is TR1. This should represent the current in anti-parallel state. Okay, so I have selected this TR1 top level, and then this current through VMDJ PSCD voltage source. This represents the current through the memory cell in anti-parallel state. So let me just plot this. And to compare this properly, we need to drag this wave shape. I mean, just click on this wave shape and just drag it on top of the first one. And it will just merge uh, those two wave shapes because in that way we can compare the amplitude, etc. So as you can see, let me just increase this size. Okay, so the red one shows the current at TR0. I mean, here we have written so TR0 means parallel. So the red one represents the parallel current. I mean the current in parallel state. So as you can see, this is higher than that of anti-parallel state, which is actually true. I mean, this does make sense because we know that in parallel state the resistance is lower and the current will be higher, and in the anti-parallel state the current will be and then the resistance will be higher and the current will be lower, and that is what is happening here in our simulation. Now we'll move to RAM or resistive RAM. This is quite similar memory cell. I mean, the structure of the RAM is quite similar to MRAM that we have just shown. Uh, Let me just draw again. So the cell structure is exactly the same. As you can see, this is the bit line, and this is the RAM. I mean, not RAM. This is the memory store. Okay, and this is the transistor, and this is the source line, and this is okay. So here, exactly in the same way, we will treat this memory store as a black box. I mean, we have a memory store model, and we will use that model as a black box, and that model will have pins and or terminals. We'll have to connect this in the circuit, exactly similar to MRAM. So let me show you. So exactly. The process is exactly similar to MRAM. I have created another folder with the name RAM, and I have uploaded these files. These files will be provided to you in the canvas. So this is our main RAM read.sp. This is our main simulation. I mean main simulation code. Let me just open it. You know how to open it, right? We have already shown in the MRAM section. So I have just already opened it in the gedit. Let me describe the code. So this code requires these two files. The first one is models design inc. So we do at first you will be given the models.zip file, and you have to unzip it. And if you unzip it, the folder will be here. So this is the models design folder. Okay, and this design model design folder actually contains the model of the transistor we will be using in this memory cell. And the second line is the second file we need is the memristor.tmo.va. This is the model file for the memristor, okay, that we will be using in this memory cell. And these are the typical options. You do not need to change anything in the options. And now let's move to the parameters. There are several parameters. This will be required inside the circuit. Okay, so at first, this is the netlist actually. So let me describe the netlist by drawing the circuit. So let me open the yeah whiteboard. Here is so let me put them side by side. Okay, so let's go to this line. So here, as you can see, in this line we are calling the memristor model that we'll be using in this code in this circuit. So we are naming this as XRHRS. So this is the name of the black box, or we are treating the model as a black box that has some terminals, and we are using this inside our circuit. So we're calling it here, and this model has actually three pins. As you can see, the first this is the first pin, this is the second pin, this is third pin. Actually these pins are connected to these nodes. Let me just go back now without confusing you. uh, let me open the model file. Okay, so this is the model file. So here, this is the name of the model. So after this is how the Verilog game model is written. So you have to write the module, this word, this keyword, and then the space, the model name, and the pins. Okay. There, as you can see, there are three pins in the memristor model, but we know that memristor is a two-terminal device, right? So it will have so these the first two pins are the two terminals of the memristor. So that means the first pin is set as P or is named as P, and the second terminal is named as N. And I can see that output resist, the third pin resist is actually an output pin. So what does this, what output does it provide? It's the name actually suggests its function. So it will return the I mean, it will show you the resistance value of this memory store. Okay, so currently the memory store we are using that has a low resistance state of nearly 3K and high resistance state at nearly 30K. So if we need to observe what resistance state it is in, we can probe this terminal. Okay, so there are three terminals, and the first two terminals are the our two. I mean, this is a two-terminal device. So the first two pins represent the two terminals of this device, and the third pin is for probing the resistance state. Okay, so let's go back to the main code. So as you can see, so the first pin is connected to a node called BLHRS on the circuit. So this pin is connected to BLHRS node of the circuit. Okay, and the second pin N is connected to NHRS of this circuit. And there is a, as I have already mentioned, that there is a third terminal pin, which is, so the pin name was resist, and this is connected to RHRS. This is kind of imaginary node. Okay, this is not connected to anywhere. This is just to probe the value of this node. Okay, so RHRS is connected to the resist pin of this memory store. Now this is the model name, MEMRTMO. And so here we are also passing some other parameters. Like the first one is form equal to 1, means that the memory store is already in formed state, so we do not need to form it, or we do not need to provide any forming voltage and etc. So it's already in the formed state. The model file is written in such a way that form equal to 1 means already formed, and form equal to 0 means that is not formed, and you have to provide forming voltage. For simplicity, we are assuming that this is all the model is, I mean, the memory store is already formed. That's why we are passing form equal to 1. And then these are other parameters like initial resistance uh, of the memory store would be HRS. We are just passing the HRS value. This HRS is actually a parameter value. As you can see, these parameters are already written here. So HRS equal to 30K. So we are initializing the memory store with the high resistance state, which is 30K. And we have to also, this is the initial resistance, right? And you can also pass the high resistance state value and low resistance state value of the memory store. Okay, so here we are passing HRS. This HRS is a parameter. So parameter value is like 30K and LRS equal to 3K. So we are passing 30K as HRS and we are passing 3K as LRS. Okay. Now let's move to this line. This is actually a transistor. This is a different kind of transistor. This is actually a bulk MOSFET. Previously, you have used uh, FinFETs. That was another model file, which was PTM-MG. But here we are using bulk MOSFET. That's why the name is like that, DGX and FET. And we are calling this bulk MOSFET file from this first line. As you can see, the models design.inc. This includes this bulk MOSFET models. Okay, so as you can see, we have named the transistor as XNHRS, whatever, and the drain is connected to the NNHRS, and the gate is connected to NG1 node and NS1, the other terminal. Let me just erase this and draw the circuit according to the code. So here, as you can see, there is another voltage source that connects the NS1 node to ground. So this is the voltage source that will connect the NS1 node to ground, because this voltage source is set to 0 volt. Okay, we have already mentioned that 0 volt voltage source actually shorts the circuit, and we can use this to measure the current through this memory cell. Okay, and then we have to provide gate voltage here. So we are just adding a voltage source right here. So the name of this voltage source is VGate1, and this is providing voltage from NG1 to, okay, no, this is not connected to ground actually. So this is connected to word line. Word line node. There we are creating another node which is called word line. This word line will be connected, but before that, we are making actually another circuit. This circuit, this circuit is in a high resistance state. Okay. And to compare the high resistance state and low resistance state, we are actually making another circuit which is exactly the same. I'm not drawing this because this is just exactly the same, but the names are changed. Like instead of HRS, the nodes are named as LRS, and as we can see, the initial resistance is also LRS, and HRS equal to HRS, because so HRS is equal to HRS because you have to pass the HRS value and LRS value also. Um, uh, and uh, and the node names are different. Like instead of NG1, we are using NG2 for that second cell. So basically the same copy, but the first cell will have HRS state and the second cell will have LRS state. Okay. Now let's move to more biasing. I mean, we have not completed the biasing scheme. We do have word line node, but and this is actually 0 volts. So this is nothing but shorting NG1 and WL. This is not actual voltage we are providing to the gate. So this is the actual voltage we are providing to the gate. So we are defining another voltage source, which is VWL, which is connected between WL and the ground or zero. And we are providing this kind of wave shapes to the word line. We are just activating the word line after a certain amount of time, etc. It's quite similar to what we have done for INRAM, and we will observe this wave shape in the wave view tool as well. And then we have to bias bit line because we need to insert the read voltage to the BLHRS or bit line mode. So VBL HRS is the voltage source that we are using to provide voltage to the bit lines. Okay, so this is also a wave shape. Okay, we'll observe this wave shape in the wave view tool as well. And the second similarly, we have to provide the voltage to the second copy of the circuit, which is in LRS state. Okay, uh, and this is just a transient simulation run. You do not need to insert this star maybe, yeah, because that's not needed. So this is what we need: dot transient simulation, and it will the first one is the state. So we will be using a step size of 0.1 nanosecond, and we will run the simulation up to 26 nanosecond. So let's run this code. Okay, so it's twice. The code name is RAM read.sb. So the job is completed, and let me open the web viewer. Okay, so just open this. So we have to select rm read.tr0. We have already selected this, and then select this, and then select top level. So what should we observe? At first, let's verify the web shapes that we provided, right? Observe the voltage of word line or WL, and let's observe the voltage of the BLHRS, BLLRS. So let's verify that. Oh, sorry. So this is the PWL. I mean, the gate voltage. This is the pin voltage for HRS, pin voltage for LRS. This is exactly the same because for every case we have to apply same amount of read voltage again. Yeah, so these are the voltages or pulse signals we have provided. Now we want to see the results. Okay, I mean, what is the result here? So let me just open the. Okay. Um, this is the circuit diagram, and we have mentioned that we have added a 0 volt voltage source. We can use this voltage source to read current through this memory cell. Okay, so let me just open that current worksheet. So we do have, yeah, so these are the voltage sources that we put to measure the current through the memory cell. So let me just open these two wave shapes, and I would like to merge them together to compare. So I've selected these two wave shapes and click right and just group. As you can see, the green one is actually the HRS state current. Okay, so HRS means high resistance state, and high resistance means lower current, right? So that is what happening here. As you can see, the in the case of HRS, the current is lower, almost near to zero, not exactly zero, but near to zero, approximately zero. Okay, and for the case of low resistance state, the current is nearly 100 and over 100 actually, or 100 microampere, right? So for low resistance state, you're getting higher current, and for high resistance state, you are getting lower current, which does make sense, right? Now, using the same code and the same circuit, we will also show you the write operation of the resistive RAM or RAM. So yeah, so this is basically the read and write operation circuit is mostly the same. Just let me show you the subtle difference. This is a lecture 13 slide for this class. I'm just going to page number 30 here. So let me just make it bigger. So here is the write operation and read operation. So what we need to change is the is the bit line voltage. Let's see actually. So we are actually providing the word line voltage and bit line voltage, right? So here, this is the left hand side is the write operation, and right hand side is the read operation. So what difference can you see between word lines and bit lines? As you can see, word lines are exactly the same wave shapes we have to provide, right? So we do not need to change for the write operation. We have already done the read operation. So uh, as the word line voltage is exactly same for the read and write operation, we are not going to change the word line wave shape, but there is a difference between the bit line voltages, right? So for the read operation, we have used a read voltage, and for the write operation in the bit line, we will have to use the write voltage. So let's go back to the code, and it is obvious, as you can see, that the read voltage is definitely small and the smaller, and the write voltage which will provide to the peak line will be very much greater. So let me show you that in that thing in the code, exactly the same code as we have used in read operation. But let's see here we so let me just open that read code maybe first. Then I will show what changes have I done on the read code to make it a write code. Okay, I mean write operation code. So in the read code, as you can see, we already have the variables. I mean the parameters vread, write. So we did not use the write for this here in the code, but we uh, kept that in the parameter list, but we didn't use it. As you can see in the bit lines, we used read voltages, vread. Okay, so vread was like zero point 0.4 volt. Okay, but we for the write operation, we just need to change this portion. So instead of read, we will be providing the write voltage in these bit lines. Okay, and the write voltage is like 1.5 volt. Okay, so I have just copy and pasted the read operation code, and I just changed this from it was vread, and I changed it to write, as you can see. So vread instead of vread, we are providing write here. Okay, so all the vreads are changed to write here. So that's actually the write operation code. So minimal change. Okay, now let's just observe the operation. Okay, so let me run the code in mobile start terminal. You can do the same thing in the real VNC terminal as well. So I'm just running the code that I have just edited. So ATSpace rm write.st. Uh, execute the code and let me observe the result as a wave view. Okay. So let me just open the wave view 2. Open the waveform. The code name was rm. Let me select it from here. So this is the rm write TR0. I'm going to open this file in the wave view. And let's go to the top level and let's check the bitline voltages. Okay. So the bitline voltages were VBL VBL So we had two cells, and in both cells we provided the same amount of voltage, which is the right voltage, which is 1.5 volt, and that should actually change the state. Let's see. So how to check what state is it? The memory cell is in now. Okay. So remember we show we yeah, here as you can see. Remember we had a third pin to probe the state of the memory register. Yeah. So RHRS. So we have connected the third pin of this memory register model to a node called RHRS. Now, if we see the value of this, I mean the voltage of this node, but remember the code, I mean the model was designed in a way that it will return the resistance value, but we are just observing that resistance value using a voltage number. It's actually confusing, but that's it because we only can see or we only can plot in a wave view only the voltages, right? So although it's actually wave view will show this as voltage, but the number we are getting from this third pin will be actually the resistance value. So this is a trick to observe values other than voltages or currents. Okay, so long story short, if we see or observe the voltage of this node, we'll get the resistance value actually. So this is actually designed inside the model file. So this was designed inside the model file. Okay, so let's observe the value of this RHRS pin or node. So let me just plot them. VRHRS, and I want to plot the other circuit state as well. So here are the wave shapes. The VBLLRS is like 1.5 volt. We are actually providing 1.5, which is the right voltage to the peak lines in both cells. So as you can see, the first cell was in high resistance state, and the second cell was in low resistance state. So here, basically, we are trying to write one in both cells, right? Suppose write one means putting the MM resistor in low resistance state. So to perform write one operation, we need to convert them to low resistance state. Uh, so here, as you can see, the second cell was already in the low resistance state. So that's why there was no change in it. But for the first cell, as you can see, it was initially in the high resistance state, and it goes to the low resistance state. So we have been able to convert two cells to low resistance state, right? Now let's move to the write zero operation. So to make this write zero, we just need to put a negative sign in front of the P, right? Because let me just open the slide here. As you can see, uh, for the write operation, write one operation, we need to provide a positive voltage, positive bit line voltage, which is plus 1.5. And for write zero operation, we need to provide negative voltage. Okay, so that's why we'll be putting negative signs in front of the bit line voltages. Okay, so we are putting negative V light voltage to the bit lines of both cells. Okay, now let's save and run this code. I'm running the same code because I edited that. Let me update the result. So you have to just click update, and all these results will be updated. So yes to all. So as you can see, yeah. So we are providing negative bitline voltages here in both cells. So this is the first cell which was initially in the high resistance state. And yeah, what was our target? To make every cell to convert every cell into high resistance state. So it was already in the high resistance state, so there was no change in it. But the second cell was in low resistance state, as you can see. And after our write operation, it goes to the high resistance state. So if we define high resistance state as zero, so here we have been able to perform write zero operation, okay, in both of the cells. So that's how write operation works in resistive RAM.